Okay, we are in Unit 2, Chapter 7, 8, 9, and 10 kind of all together. Kind of doing an overview here, and we finally figured out how to find our regression line with the calculator, in case you forgot, but then we also set it up with our diagnostics. Take a look at the last video in order to do that, so we can get our R and R squared, our correlation and determination. So, again, if I'm moving too fast, you need to pause these videos and you need to write the stuff down as you go. If I continue to talk at a much slower pace, the videos would take hours upon hours upon hours. And they already do take that long. So, anyway, using a calculator, we find the correlation to be this, right? The correlation of determination is R squared, which is 0.78 roughly, 78%. This indicates that 78% of the variation in the number of policies is accounted for by the variation in the number of minutes. And that is comparing, for those of you that don't know, to this. So if this was the problem, I plot this all, I do all this. And they're saying, hey, that's the R that we found. It says that 78%, as we do the R squared, 78% of the variations of the X accounted for the Y. And the X, if you look, was 78% of the minutes per potential customer, right? The policy of minutes is accounted for by the variation in the number of minutes, or vice versa. It indicates that 78% of the variation in the number of policies is accounted for by the minutes. Depending on how you want to write it, oftentimes people do write the Y first by saying 78% of the variation in number of policies is accounted for by the variation in the number of minutes. So, take a look at this. That is one way that we told you that you could write the regression line as point slope. That's 12. There's your slope. All right. There's your X value, right? And then they take it through, and then they combine to get this. It says we also could write policies equals, because that's what we're trying to figure out, because that's the Y's, right? Policies is your Y's, and the minutes were your X's. So adding this to our scatter plot, that is where that gets. That's why that's there. It's a predicted equation. So although the overall pattern is positive, right? The overall pattern is positive, given any 2 points, it's still possible for the first point to have a larger X value and a smaller Y value than the second point. It's still possible. Okay? That's still possible, meaning that it looks like a majority of them are positive. 78% of them are still positive, but there's still a possibility that that might not be the case. Okay? So, alternatively, we could say 78% of the variation in the number of policies is accounted for by the least squares regression line. 78% of the variation in policies is accounted for in that regression line, right? So, for example, we might predict that agents who average 24 minutes per customer, so 5, 10, 15, 20, 25, so the average 24 minutes per customer will average up here 5, 10, maybe 11 to 12-ish, maybe. Any number from, and that should be before. There you go. And remember from before, we have this, right? So we already have this, so that's our predicted line, all right? And it's good for about 78%, all right? So 78% of the number of policies can be basically explained by the minutes per potential customers. If we plug in 24 into this, I get around 11.45. And if you just look at this, around 5, it's 10, 15, 20, 25, look, it is pretty close to 11.5, 12, right in there. So, I mean, it's about what we said we would get when we plug it in. Thus, you should get about 11.45 sales per week. We also note that each additional minute spent seems to produce an average of 0.5492 extra sales. For every extra minute, it's about how much more sales they'll get. So let's look at another example. Following are advertising expenditures and total sales for 6 detergent products, right? 6 detergent products. This is advertising sales, total sales, right? So, predict the total price. If $5,000 is spent on advertising and interpret the slope of the regression line. Well, we have to plug these in to figure it out, so if you got to pause the video to do so, I recommend you do that. And what if 100,000 is spent on advertising? So we'll come back and answer these. So first of all, let's use the calculator. I go to Stat and Edit, and I need to plug my values in, right, in our list 1 and list 2. So clear out what you had in there before and plug these values into your list 1 and list 2. Afterwards, you press Stat again, press the arrow key over to highlight calc, and we want to find our line reg, list 1, list 2, and we calculate it, and here we are. So, we are looking at our R, which is basically like what we have here. This is the line, that regression predicted line, but right here our R squared. That's our correlation of determination that we are looking for. Okay, and in doing so, that helps us out to see that about 85% of the Y can be explained due to X, is what we know, which is pretty good. I mean, so in our equation, 85% of the Y can basically be explained by the X when we plug that in. So if we plug in 5 instead of 5,000, because everything is in terms of thousands, so I plug in 5 instead, and because it's all in terms of thousands, if I plug in 5, I get roughly this, which as in thousands, I get 96,158. Would be what I get predicted wise, and that should probably just have a hat over it. And now if 100,000 was spent on advertising, I would plug in 100 since it's by thousands, and I would get roughly that, and that should be another, this is a predicted equation, not the actual equation, so put a little hat above your Y, and we end up getting around 789,183, so we're able to figure it out. That's our prediction. But the issue now is, how much confidence should we have in this answer? That's the key, right? So those are the answers, but of the predicted, that's what we're predicting. But how much confidence? To be honest with you, not much. And here's why. Because we're trying to use the regression line, right? The regression line to predict values far outside the other data points. Now here's the key. This is what kids have a hard time doing. You have a line that is used to predict what outcomes might happen, but it can't predict something way, way, way out there because we don't know the trend. The graph and the points that you're zooming in on, the values that you have, I don't know if something's going to drastically change the higher up they get. It might stop being linear. Maybe for some reason a different trend happens, like we elaborated with. Maybe a different cluster happens and it clusters down for some reason. We don't know what's going to happen. So because I don't know what's going to happen, I can only account for and predict things within the range that we were given for the most part. And to be honest, you can predict a little outside, but I mean, by a little, I mean a little outside. So our X values are from 2.3 to 6.2, right? Anything in between there, you betcha, right? You bet. We can use our regression line to predict that, right? 5 is within our bounds, so that is okay. That one we can use. That one's good. But 100's way out there. I don't know if it's still going to hold that same pattern, so I can't use that. It's too outside of our area. So we can only accurately predict using a regression line if it's within or around our X values. And this procedure is basically called the extrapolation and must be used with great care. Okay, it's got to be. And again, following up with some more trick questions that you get on your AP exam to follow if you really understand not just the math and plugging things in, but the concept. All right, these AP exams are so much about the concepts of this stuff. Do you really grasp, hey, I can find a regression line, but can it even be used? And why? All right, that's what they want to know. It should be noted that when we use the regression line to predict Y values from a given X value, we are predicting the mean Y value, right? The average Y value. That's why it's a predicted line. It's not the actual accurate thing. All right, it's the mean of those that could possibly show up. That gives us our X value. For any given X value, there are many possible Y values, and we are predicting what their average is going to be. So if 5,000 is spent many times over and over and over again on advertising, right, various resulting total sale figures may result but those average should be around 96,158. So try this example. A random sample of 30 U.S. farm regions surveyed during the summer of 2003 produced the following statistics. All right. Average temperatures during the season were this, and their standard deviation. Great. Okay, so we got the average temp and the standard deviation. The average corn yield was this, and that was the standard deviation for that. And I know the correlation. Now, this is why I told you to remember that formula for slope, because now they're giving us the averages, and they didn't even give me the total points. And based on this study, what is the mean predicted corn yield for a region where the average growing season temperature is 76.5? Okay, well, we can change 76.5 into a z-score, right, because that's degrees, to relate to both temperature and the corn yield is what we're going to have to do. So let's change it into a z-score, because once it's a z-score, these are two different things. We're talking about acres, we're talking about temperature. So if I create this in terms of z-scores, I can compare them both. So if I change it into a z-score, I know the average, the standard deviation. So now that compared to a z-score is negative 1.5. So we can change that 76.5 degrees into that, negative 1.5. Standard deviations above that. With the correlation being R equals 0.32, the predicted corn yield is correlation times z-score. So to find the predicted corn yield, I'm giving you this formula to help you figure out what the other z-score is. It's correlation times the z-score. Well, were we given that? Yeah, we were given the correlation right here. All right, is time the z-score. We can figure this out. All right. So we can in turn take the correlation times the z-score to figure out, well, that's negative 0.48 standard deviations below the mean. So now I have what the z-score is of that as well. And this is another little formula that's definitely very helpful for you to remember. So now I have the z-scores of each. So if the z-score for temperature is negative 1.5 and its correlation is 0.32, that is how we can figure out the z-score of the compared list, or in this case, the corn yield. So next we can figure out how roughly many bushels per acre by using that formula. All right, by using that formula that we basically have, because that is the formula for z-score basically, right? I can find that z-score because I just found the standard deviation, right? By saying, hey, I know the standard deviation of this. I now know the mean of that other value. So we can in turn figure out what that corresponding value would be. So that corresponding y value of bushels would be that 128.6 bushels. And alternatively, we could have found the linear regression equation to relate these as well, because we would know the slope. I know the R, I know the standard deviation of both, so now I know what the slope of the line is going to be as well. So I could plug that in, and then I now know that y is this, and I now know that when we plug it in, if I know the slope and I know that value, I can then in turn figure out the missing values as well, right? To figure out where the y-intercept is, because now I know the slope, I know my points. So when I plug this in to try to solve and move it over, I get 87.827, and now I know what the equation of that line is, making that equation. All right. And since 76.5 is our x value, or our temperature, we can plug in our x value to get out our y value of corn yield that way as well, by plugging it in to also get the 128.6. When I come back here, I will take a look at the residual plots.